This is a short video about section 2.5 in Stein's book on elementary number theory, and we're going to talk about the first part. The whole section is about the structure of the group Z mod PZ star. Remember that this is the group of units in Z mod PZ. So the main result that we're going to do, where of course you could take P to be a prime number, but anyway, back to what I was saying. The main result we're going to look at in this section 2.5, what it all kind of culminates in, is that this group is always cyclic. Now, what I want to do is tell you what a cyclic group is. So if you've had some modern algebra or abstract algebra, you already know what this is, but I'll say it a little bit more generally because it's more of a group theory thing than it is anything for necessarily just Z mod PZ or Z mod PZ star. So I'll say G is a group, and I'll use like multiplication as my, I'll denote my operation as if it looks like multiplication. So I'll use exponents. So let's say G is cyclic. That means that there exists some element A in G such that the following happens. For any other element G in G, there should exist some natural number K such that A to the K gives you G. So what I'm trying to get across is that every element of G is really just a power of A. So this single element A, in some sense, generates every single other element of the group, and you'd call such an A a generator. So now let's do maybe two concrete examples before we go any further. So don't look below, don't look at primitive root yet. I'm not talking about that yet. I'm just trying to talk more about cyclic groups. So what I'm going to do is I'm going to compare the following two groups, Z mod 8Z star, and I'm going to compare it to Z mod 7Z star. And I'm going to try to look at which one of these is cyclic. Are they both cyclic or neither cyclic or what? And you could do these by hand. Essentially all I'm asking you to do is list the elements in each group and just start computing powers of each element. If you have a single element that will, when you take powers of it, you get every other element of the group, then that means it's cyclic. Now I'm going to show you how to do that on Sage, just to kind of, again, demonstrate the novelty of Sage, why it's pretty cool. So what we're going to do is, let's start with Z mod 8Z. So R is equal to the integers, so I'm just naming it R, integers 8. So remember what that does. So R is the ring Z mod 8Z. Now I just want to look at the multiplicative group of units. So I'm just going to name that R underscore units. And how do I make those? So the way I'm going to make them is I'm going to make them as a list. So I'm going to look at X for X in R if, so I only want the following X's, if the greatest common divisor of X with 8 is 1. So remember the group of units mod n are exactly the elements that are relatively prime to n. So in this case, I expect this to spit out 1, 3, 5, and 7. Those would be the things in Z mod 8Z that are relatively prime to n. Okay, cool. And so this is the multiplicative group Z mod 8Z star. All right, and so let's see. I probably need to actually call it R underscore units. And I expect it, cool, it gives me 1, 3, 5, and 7. So anytime you see R units right now, that's the group you're thinking of. 1, 3, 5, and 7. The operation is you're multiplying things, but you're always reducing everything mod 8. So what I'm going to do now is I'm just going to compute the order of each element in this group. And the way that I'll do that is with like a for loop, say. This is one way to do it. So I could do it all at once. Again, just the novelty of Sage, being able to do some of these computations all at one time. You could say something like for X in R units. So what this is going to do is I'm about to cycle through 1, 3, 5, and 7 and do the following to each element of 1, 3, 5, and 7. Here's what I want to do. I want to print X, and then right next to it, I want to print the order of X. So X dot multiplicative underscore order. Leave those open. So again, what this will do, this computes the order of each X in my Z mod 8Z star. So let's take a look at what does this look like. Whoops, that's not what I wanted. How about now? Cool. So the first column are the 1, 3, 5, and 7. That is Z mod 8Z star. And the second column is the order of each element. That's how you should read that. 1 has order 1, 3 has order 2, 5 has order 2, 7 has order 2. Okay, cool. So if you think about it, what does that say? That says that each element is really like its own inverse. Like 3 times 3 gives you back the identity. It's how you should read the order of 3 is 2. So in particular, it's not possible. Like I can't take powers of 3 and ever get 5 or ever get 7. I can't take powers of 5 and ever recover 3 or 7. And I can't take powers of 7 and ever recover 3 or 5. So this is not cyclic. So what this shows that Z mod 8Z star is not cyclic. So what I'm going to do is a similar computation with, let's compare it to Z mod 7Z star. So I'll name it S now. So let's say S is integers 7. And I won't comment as many things this time since it's the same idea. I'll say S underscore units. That's a good name maybe. And I'll use X again. X for X in S if GCD. Now I want X and 7 to be 1. So what this does, S units now, I will comment this. This is the group Z mod 7Z star. And I just put the little caret there to indicate the asterisk is up in the exponent. And I'm going to do the same thing for X in S units. I'm going to print X, comma, X dot multiplicative order. And let's see what that does. Okay, cool. So by the way, maybe what am I looking for? Maybe you can't tell. Like, well, how do I know what I'm looking for? How do I know what's a good exponent? Like 6 looks like a pretty big exponent. Is that cool? Let me give you another way to try to find this one. So I'll try to do this a little bit more explicitly. So what I'm actually going to do is I'm going to go ahead and show you what the power of each element is. By the way here, let's see, what should this be? Maybe it would be good. So this is, which is equal to, like as a set, this would be 1, 2, 3, 4, 5, 6. So those are the numbers that are relatively prime to 7 that are less than or equal to 7. So those are the things I'm going to take powers of. So now I'll come back down here. What I'm going to do is I want to just show you what happens when you start taking powers of 2, what happens when you start taking powers of 3, etc. And the question is, do the powers of 2 give me 3? Do they give me 4? Do they give me 5? Do they give me 6? If the answer to that is yes, then 2 is a generator. So let's do that. So what I might do, you could do that by hand. That might be a lot of work. I'm going to do another for loop here. So for k in range, say 1 to 7. So why do I do 7? If you look at that group, it has 6 elements in it. So Euler's theorem told me the power of any element. If I raise an element to the power of 6, then that should automatically get me back to 1. So the biggest exponent I need to consider is 6. So I put 7 just because Sage doesn't include that right endpoint. So if you push enter again, it should indent. And here's what I want to do. I'm going to print something like X, and then comma. I want to actually show you the symbol. I'm going to raise it to, comma, and then I want K, comma. I want to actually show you the symbol that it's equal to. So I'm just going to plop that down as a string. If that makes any sense to you, cool. If it doesn't, don't worry about it. And then I want to compute the actual power here. So let's see what this looks like. All right. So, the first set of blocks there, you see 1 raised to the 1 through 6th power gives you 1. So let's look at 2. 2 is the first interesting one. When we start raising 2 to different powers here, I see that it just keeps bouncing back between 1, 2, and 4. So 2 is not a generator. Let's take a look at what happens when I start raising 3 to that power. Then what do I get? I get just 3, 2, 6, 4, 5, 1. Oh, so check out 3. If you zoom in on that, but the powers of 3, if you look what's going on in the equal sign to the right, I recover 1, 3, I guess maybe I should start. I get 3, 2, 6, 4, 5, 1. That is all the elements that are in the group. So that shows that 3 is a generator. So what does this demonstrate? So this tells us, from this we see, oops, I gotta scoot over, don't I? So this shows that 3 generates the group. So in that case, this group, Z mod 7Z star, is cyclic. Great. So cyclic's a cool property because in some sense, you really just need to tell me about what's going on with the generator, because everybody else in the group depends on just what the generator does. Okay, so in this same video, I'm going to tell you about something that's related. And the relate on a similar idea is what's going to be called a primitive element. And again, I'm relaxing the condition that I need the modulus to be prime just for any n. So just by definition, a primitive element modulo n, it should be an element of this multiplicative group that has order phi of n. So in the examples that we've done so far, in our case, we just saw that 3 had order 6, right? Because 3, if you look at 3 to the 6th, is the first time that you ever get 1. So 6 is the smallest exponent and smallest natural number exponent you could raise 3 to in order to get 1. So 6 is the order of 3, so 3 would be a primitive element. Whereas in our example that we did earlier with 8 here, you know, if I was to actually write this out, you know, what is this? We said that this should be the group or the set 1, 3, 5, 7. And the question is, do you have an element that has order 4, right? That's what phi of 8 is. It's 4. And in this case, no. The order, if you look at this list here, the highest order of an element you get is 2. So this group does not have a primitive element. So a big question is, how do I know when something like Z mod NZ star is cyclic? And how do I know when something like Z mod NZ star has a primitive element? Let me also show you in Sage, there's a way to check for primitive elements, kind of similarly to how I was doing stuff for cyclic groups, but maybe it'd be good to take a look and say how to do that. And so, let's see, I mean, you could also just see from, well, I'll just go ahead and do it. Why not? This will be good. So let's take a look at, let's say R, let's rename it now. Let's say R, and let me give myself some space. Okay, let's say R is, and let's relax the condition that your modulus is prime. Let's do 9, say. Let's say R is integers 9. Oops. All right, cool. And I'm going to do the same thing where R units is equal to X for X and R if, remember, I want the units, so those would be the numbers that are relatively prime to 9. So GCD X9 is exactly 1. And what should those be? Let's actually call it just so you see it. So that's what R units actually is. So what I'm going to do now is I'm going to check, is there a primitive root in there? Remember, what I'm asking is, do any of those elements actually have order 6? And how do I know it's 6? Well, because I can count that that's how many elements are in the set. Or, remember Sage can do, what is Euler phi of 9? And I know it should be 6. And you see 6 showed up right beneath my list there. So do we have an element of order phi of 9, which is 6? And the way we'll do this is for X and R units. And then I will say print X, comma, X dot is underscore primitive underscore root, and those. So is underscore primitive underscore root is like some attribute that you can put on X, just like how finding its multiplicative order was. And what this spits out is, if it's a primitive root, it says true. So how should you take that? That says 2 and 5 are primitive roots. And so 2 has order 6 and 5 has order 6 is another way that you could see that. There's one more thing. If you look in the book, it tells us one more way to find primitive roots in Sage, if you scroll down here. But just be careful. You notice it's a different function. So print the prime and print primitive root p. What that's going to do, though, is that's going to give you the smallest positive primitive root modulo n. It's only going to give you the smallest one. So for example, if you were to do that here, it would only give you 2. It would leave off 5. So maybe this is a good way to check what all the primitive roots are in that particular group.